These are the frequently asked questions for pre-calculus for section 1-2, day 2 worksheet, where we're working on vertical asymptotes, jumps, and well, discontinuities if there are any, and then we have piecewise functions. So I've been asked to look at B, and for B, when we look for our vertical asymptotes or our holes, we go to the denominator and try to make it equal to 0, but we realize that that is going to mean imaginary numbers, and we don't graph imaginary numbers on our real number plane, our Cartesian coordinate plane. So with this one, we get absolutely nothing before we start this, except maybe you might want to throw a 0 in here real quick just to see, table-wise. If we put a 0 in, we'll get -5 over 25, which is -1/5. So 0, -1/5 is right about, there or so. And you realize you need to grab a calculator with this one. So what you're going to have to do is absolutely make sure that you use parentheses for your numerator and your denominator and type this one in. And then to get a little better look at it, you might want to manipulate your window a little bit. So that will mean, let's see, you're going to want to see more of what's going on with your x's. Make your x min a -1 and your x max a +1. And you're going to see that this graph is very, very close to the x-axis, dips down just slightly before that 0, -1/5, and then comes up on the other side of the axis, but again, it is hugging that x-axis. So without changing your window, it's almost impossible to see the graph itself. But then you realize, we don't have any holes, vertical asymptotes, or jumps on that. It just is not going to happen. Then down for E is the next one that you had questions on. So E, we have a piecewise function. And for this one, what we see is that different things are going on if you use 3 and if you don't use 3. So the first thing I would do is come down to this line and say, okay, well at 3, it's going to be 9. So go to 3, 9, and make a dot. Then for the rest of the graph, because it says when x is not equal to 3, we're supposed to do x squared. So that would be 0, 0, 1, 1, 2, 4, 3, 9, but 3, 9 is already a part of our graph. Get some more points on here. So this portion of the graph is just our normal parabola. But notice, even just using that different color here, you can see, we had to stop and put x = 3 at 9. Well, it was already part of the graph, so it was already included. But the coloring here will show you that came from the second piece of information on E. Then for F, similar situation, except x = 3 is now down here at -9. So down here. And that means that's going to leave us a hole in our graph, because our normal graph for that parabola, let's see if I can get these in the right spots, would go through 3, 9. However, that is now, that hole is filled by that red dot down below. And that is because the first line of information said when x is not 3, just graph x squared like normal. But when it is 3, we have to go down here and graph -9. So that is F. And then on the back side, the next one you asked about was G. So G, our separation is absolutely taking place at 3. We can see that. When x is less than 3, we're supposed to do one thing. When x is greater than or equal to 3, we do another thing. So I put in my line of separation. Again, that is not part of the graph. I know I have 0, 0, 1, 1, negative 1, 1, 2, 4, and I just keep putting those points in using symmetry, realizing that that said less than 3. So this graph works for these x values because these are x values that are less than 3, but once I get up here, I have to have an open dot. And that's because I was only supposed to graph that parabola when x was less than 3. Now from that point, what I'm supposed to do for x is greater than or equal to 3 is 5x minus 6. And for this one, you might just want to make this a little easy on yourself and just go ahead and put in some numbers like 3, 4, and 5 that are greater than or equal to 3 and see what you get. So 15 minus 6 is 9, 20 minus 6 is 14, and we can see that this graph will include that 3, 9 that we have right here. But of course, you know, for 14, it's going up a little bit faster than we can graph here. So it'll be a straight line off of that point. But again, that's not a hole. It did get filled. It was filled not by the parabola, but by the line. And that's because we do have an equals bar right here. So we do want to include that point. And then another one that you had asked about was J. All right, the last one here that you asked for was J, and J definitely has a split at x is greater than 1. So we have a split here, and I started thinking about what's going to happen, and I want to take a look at this top and bottom piece. But the top piece, that is our parent function for a hyperbola, and 1 over x. That piece is only going to happen when x is less than 1, which is the left side of this graph down here. And what we have to do is remember, hey, we put in a negative 1, we're going to get negative 1. We put in a negative 2, we're going to get negative 1/2. So that is just a branch of a hyperbola, and that's what we get for that side. In fact, that branch is never actually going to cross the y-axis there, because as we put fractions into that, like negative 1/2, if we put negative 1/2 into 1 over x, we get 1 over negative 1/2, which we don't multiply, or we don't divide by fractions, we multiply by the reciprocal. So that would give us negative 2, and it just starts to drop down. So then the interest would be, you know, what's going on between 0 and 1, and then how about after 1? You know, what's happening after that? So we go down to the bottom portion of this problem, and we see that that is factorable. And what that tells us is this. First of all, this top fraction from the denominator is going to have a vertical asymptote at x equals 0, and that's why that's not going to cross the y-axis. This one is going to have a vertical asymptote at x equals negative 4. But that doesn't matter in this problem because that fraction is only used when x is greater than 1, so we don't need that information. But we do need that there will be a hole at x equals 3. So what we need to do is figure out really what's going on between 0 and 1, and then from 1 on. So between 0 and 1, we have fractions. So what we would want to do is just take some fractions and put them into the function that they need to go into and see what we get. And that's going to be right here because we are still less than 1. And so once we do that, if we put in a positive 1/2, we get 2, and a positive 1/3, and we get 3, etc. And we see that that graph is just tucked really, really, really closely to the x-axis until we get right there. And we know we can't include that point, and that's because we do not have an equals bar on either one of those two conditions. And then the next piece would be, well, what's going to happen with this as we go further and further out to the right? So we could put in some numbers. We could actually graph x minus 3 over x squared plus x minus 12, take advantage of the table to look at what happens when you put a 2 in, a 3 in, etc. And what ends up happening is it's going to use that x-axis as an asymptote. But what we have to remember is This x equals 3, that's going to end up being a whole because these two would cancel out. So when we get to 3, we need another whole, and then we'll go off forever to the right. So a lot of interesting things going on in that last one. And again, you can always, grab your calculator, only look at the table function for the numbers that are less than 1, and then graph this one and only look at your table numbers that are going to be greater than 1, and that would kind of help you get those. But in the end, we would like to be able to just plug in a few numbers and see what we get for this visually.